Alongside this magnetic activity come convulsions of plasma, as huge mountains of it, half the size of a planet, rise up and collapse in a matter of hours. Before long on our journey southwards, we encounter our first granule, one such chunk of erupting sun stuff. There's bound to be some turbulence in this region, which spans some 1,500 kilometers. It will take most of a day to make the crossing. After a few days, we reach our first sunspot. A massive cavity opened up in the sun as immense magnetic fields punch down through the plasma, a yawning chasm 1,000 kilometers deep. This one, however, is roughly medium-sized, just over the width of the Earth. At our sensible speed, we will reach the other side in a few days, if we don't stop for toilet breaks or sleep. As we crawl onwards, we are met with prominences and flares. Great arching structures as magnetic fields funnel stellar material out into space. These eruptions are unpredictable, and at their peak, they can stretch for 1 million kilometers or more into the darkness before plunging back down, taking up so much volume that they could cradle all the planets of the solar system in their embrace. And yet, we've barely gotten started. At the present pace, our craft will reach the equator of the Sun, completing a voyage of a quarter of its entire circumference in a little over a year. Best to bring a snack. Ancient people believed that the Sun and the Moon were the same size, and in a sense, they are. By sheer cosmic coincidence, the Sun is roughly 400 times wider than the Moon, while sitting roughly 400 times further away. And it is because of this coincidence that Earth is the only planet that gets to enjoy perfect total solar eclipses. And yet even at the great distance of 150 million kilometers away, the Sun is still powerful enough to melt the ice in your drink on a warm summer afternoon. Indeed, it's for the best that the millions of kilometers between us are nothing but vacuum. If the sound produced by the Sun could reach the Earth, it would be louder than standing next to a jet engine during takeoff, every single second of every single day. This is because the Sun is by far the largest object in the solar system. In fact, from a certain perspective, the Sun is the solar system, with all the planets, including Jupiter, nothing more than rounding errors and extra decimals added onto the mass and radius of our parent star. The Sun alone contains 99% of all the material in the system. 1 million of our Earths could fit within its volume, and even mighty Jupiter can do nothing more than barely nudge and tweak the position of the Sun as it orbits around it. Indeed, the Sun is roughly 10 to the power of 44 Planck lengths across, the Earth roughly 10 to the power of 42. But why is the Sun so much bigger than the Earth? Well, as with all the layers that came before, the answer lies at the intersection between two competing forces. In Sudbury, Ontario, in Canada, over 2,000 meters beneath the Earth's surface, sits an unused mine shaft. No sunlight pierces these depths, just the warmth of the surrounding miles of rock, bringing the temperature of the mine shaft to a sweltering 50 degrees Celsius. And at the center of an otherwise empty chamber is a strange piece of technology. It looks like a sort of cosmic egg left long dormant. But this was not the work of aliens. It was built by astronomers. And yet the instrument had no mirrors, no lenses, no refractors. Indeed, it couldn't even see the sky, but it could peer right into the heart of the Sun. And in May 1999, a team of astronomers activated it. The observatory consisted of a geodesic sphere containing 1,000 tons of heavy water, donated to the experiment by Atomic Energy Limited of Canada at no cost, and a market value at the time of over $330 million. Mounted across the surface of the sphere were 9,600 photomultiplier tubes, each one designed to amplify any feeble flickers of light within the water. This was the Sudbury Neutrino Observatory, which for 7 years watched as tiny, ghostly particles streamed through it. The observatory had been designed to solve a decades-old mystery about the Sun. At the opening of the nuclear age, physicists had realized that fusion powered the core of our star. Every fusion reaction produces a neutrino, the tiniest of the fundamental particles. Indeed, every single second, hundreds of trillions of solar neutrinos pass through your body. But previous experiments could only detect roughly 1/3 of the expected amount. Did this mean that the Sun was actually 2/3 smaller than it seemed? No, of course not. The answer lay within the neutrinos. Neutrinos come in 3 types, known as flavors, and unlike previous experiments, the Sudbury Neutrino Observatory could measure neutrinos in 2 ways. It could detect just one flavor, but it could also simultaneously measure the total number of neutrinos passing through. And after years of analysis, the Sudbury Neutrino Observatory demonstrated that neutrinos could change flavor as they travel. This experiment rocked the physics world and created a mystery known as neutrino oscillation that persists to the present day. But it also confirmed that fusion, and fusion alone, makes the Sun shine. Every single minute, the Sun consumes roughly an Earth's worth of hydrogen, fusing it into helium in the core at a temperature of roughly 10 million Kelvin. Each conversion leaves behind a little bit of mass, which translates to a little bit of energy. Multiplied again and again, the Sun produces more energy in a single second than the entirety of humanity uses in 100,000 years. And so as the massive weight of the Sun, the force of gravity, pulls inwards, resisting that is the energy released from fusion, which pushes outwards as the flood of radiation tries to escape the core. Ever in balance, the 2 forces maintain equilibrium, with one never quite winning the battle against the other. This balance, however, does mean that stars can only exist in a certain range of sizes. At the small end are the red dwarfs, stars so small and dim that their feeble light is mostly in the infrared region of the electromagnetic spectrum. The smallest known star is EBLM J0555-57AB. Sitting about 600 light-years away, the star is only about 88 times the mass of Jupiter. It's right at the limit. Any smaller and its own gravitational pull would be too weak to ignite fusion in its core. It's less than 1/10 of the mass of the Sun, and it's so small that it only has a radius roughly the same as the planet Saturn. Smaller than this are the brown dwarfs, strange hybrid objects that straddle the ambiguous boundaries between planets and stars. Shortly after formation, they briefly fuse deuterium in their cores, but then they sputter out, spending the rest of their lives merely cooling off. Red dwarfs are by far the most common kind of star. Roughly 2/3 of all the stars in the Milky Way are red dwarfs, and even the nearest star to the Sun, Proxima Centauri, is a red dwarf, but it's so dim that it's invisible to the naked eye. And at the other end of the spectrum are the true giants of the galaxy, the largest stars. The biggest stars are so big that it's difficult to ascertain their true extent. Their surfaces are bloated and extended, constantly in flux as they swell and contract in violent spasms that reveal their inner nuclear turmoil. Along with that, their brightness changes over the course of days, making it extremely difficult to measure for sure. And when it comes to the most massive, most luminous, hottest star known, analogy fails. Sitting 136,000 light-years away, R136A1 lives in a satellite of the Milky Way, the Large Magellanic Cloud. It weighs nearly 300 times the mass of the Sun and emits so much light that it outshines 1,000,000 suns. But it's so hot that most of its output is in the form of ultraviolet radiation. Indeed, to the naked eye, R136A1 is only 164,000 times brighter than the Sun. At the distance of Proxima Centauri, just under 4 light-years away, it would outshine the full moon. R136A1 exists right at the limit of the most massive star possible. This is because heavier stars have more gravitational pressure in their cores. More gravitational pressure means a higher rate of nuclear fusion. More nuclear fusion means more radiation, and more radiation means more energy poured into the body of the star. At a mass higher than 300 solar masses, the core of any star would produce so much radiation that it would blow itself apart in a furious burst of energies, something akin to a supernova explosion at the moment of its birth. However, that's just the limit today. Modern-day stars contain traces of elements heavier than hydrogen and helium. These elements absorb light, affecting the delicate balance between gravity and radiation and governing stellar sizes. But in the early universe, the first stars had no such limits, and astronomers believe they may have swelled to sizes 10,000 times the mass of our Sun or more. There are only two kinds of objects larger than stars in any galaxy, and they represent the start and end stages of the dance between radiation and gravity that makes them possible. Stars emerge from giant molecular clouds, vast complexes of gas and dust that drift loosely through the galaxy, barely held together by their own gravity. When perturbed, a gas cloud contracts under its own weight, producing dense pockets that eventually reach the critical densities needed to ignite nuclear fusion. Indeed, a single cloud has enough material to produce hundreds and even thousands of stars. The largest known cloud is called Sagittarius B2, which stretches 150 light-years across, or roughly 10 to the power of 18 meters, and weighs 3 million solar masses. Located near the center of the Milky Way, Sagittarius B2 is also home to the other largest object in the galaxy, Sagittarius A star. This is a supermassive black hole, the ultimate end result of a star's life when its nuclear fuel is extinguished and gravity finally wins. Sagittarius A star is the largest of the black holes in the Milky Way, weighing a tremendous 4.5 million times the mass of the Sun. And so, an apple the size of a star, roughly 1 billion meters across, would not last very long as an apple. Almost immediately, the force of gravity would take over, compressing the core of the apple to nuclear densities. Once fusion ignites, the temperatures of the rest of the apple would climb to thousands of degrees, turning it into a plasma. For millions of years, the competition between radiation and gravity would keep the apple at a stable size until the light would give out and gravity would finally win. And indeed, when it comes to even larger scales, gravity almost always conquers all. Almost always. I have looked farther into space than ever a human being did before me. William Herschel was born in 1738 to Isaac and Anna. His father was an oboist, his brother was an oboist, and William was an oboist. Although to be fair to William, he was more than an oboist. He also played the violin, harpsichord and organ. He composed 24 symphonies as well as concertos and church music. But he was also ambitious, always scheming and plotting to advance up the social ladder. And so, in addition to his musical pursuits, he also decided to engage in the most gentlemanly of trendy pastimes: astronomy. He built his own telescopes, ground his own mirrors, and proceeded to make his mark on the stars. Quickly, he racked up achievement after achievement, including discovering Uranus, spotting new moons of Saturn, and recording the seasonal changes in the Martian polar ice caps. But this was still not enough. And as a final crescendo to his astronomical career, he attempted to create a map of the entire universe. To make this map, Herschel assumed that the stars were all the same brightness, and by looking in particular directions, he would measure the total brightness, giving him an estimate of the distance to that location in the universe. For the time, his map was astonishing, revealing a picture of a flattened, elongated universe, the precursor of our present understanding of the disk of the Milky Way galaxy. If only that oboist could see the maps we make now. And in 2022, after several years of operation, the European Space Agency's Gaia satellite released the largest catalogue of stars ever produced, standing at nearly 2 billion. It was an incredible number, and yet less than 1% of all the stars in the Milky Way. Spanning over 100,000 light-years, containing over 1.5 trillion solar masses of stars, gas and dark matter, and roughly 10 to the power of 56 times bigger than the Planck length, the Milky Way is, as galaxies go, rather average. Indeed, it is dwarfed by our nearest neighbour, the Andromeda Galaxy, which hosts an estimated 1 trillion individual stars, more than double the Milky Way. 220,000 light-years across. If you travelled at the same speed that took our car many months to make progress across the face of the Sun, you would have to drive for well over 1 trillion years to make it from one end of Andromeda to the other. And indeed, the largest galaxies make even these giants seem tiny. At the centres of galaxy clusters sit their most massive concentrations of matter, the brightest central galaxies. These are the downtown cores of the cities, filled with stellar high-rises and super-tall skyscrapers. The largest of these galaxies is known as ESO 38376, a galaxy so enormous that it defies description except by bare numbers. It spans 1.8 million light-years in diameter and weighs up to 10 times as much as Andromeda. A crossing here would take 20 trillion years, more than 1,000 times the current age of the universe. Galaxies are what happens when gravity, by far the weakest of the forces, has time enough to play. In a way, at large enough scales, no other fundamental force matters. The universe is on balance electrically neutral, and so the electromagnetic force holds no influence. And the strong and weak nuclear forces are limited to subatomic scales. They can't influence anything beyond their minuscule borders. And so in terms of fundamental forces, gravity, and only gravity, shapes the grandest structures in the cosmos. All it takes is time. For gravity may be weak, but it is persistent. All it takes is the tiniest seed, a small difference in density. That small seed will attract its surroundings, helping it grow. With even more mass, the pull becomes stronger. More and more, the rich growing richer. Over millions and billions of years, the universe assembled the galaxies out of the thin, uniform fog of the primordial cosmos. And gravity is not yet done. For beyond the bounds of the Milky Way galaxy sit structures that seem to embrace the heavens themselves, grand walls and glittered canopies spanning tens of millions of light-years on a side, the culmination of billions of years of gravitational effort. Surrounding the Milky Way is a ring of 12 galaxies, each sitting roughly 12 million light-years away. These galaxies are the nearest portion of the local sheet, the Great Wall in which our galaxy is embedded. Indeed, they are simply the nearest edge of that sheet, but their circular arrangement around the Milky Way has inspired astronomers to give them a name of their own: the Council of Giants. And in July 2020, an international team of astronomers discovered something even larger. Using archival data from the Spitzer Space Telescope, the team managed to pick out dim galaxies peeking through the so-called zone of avoidance, the region of the wider universe that sits beyond the dense veil of nebulous gas in the core of the Milky Way. Through there, they identified a structure almost beyond description. Called the South Pole Wall, it is a filament of hundreds of thousands of galaxies extending for over 1.3 billion light-years from end to end. To get a sense of its extent, its ends are anchored behind constellations in two different hemispheres, Perseus in the north and Telescopium in the south, which were a full 145 degrees apart, nearly on opposite sides of the sky. If we were to drive the full length of the South Pole Wall, it would take 1,000,000 trillion years. And it might be bigger. The astronomers involved in its discovery admit that they don't know if they've completed their survey. "We are early explorers of the cosmos," said lead astronomer Brent Tully of the University of Hawaii. extending our maps into unknown territory. And so, just how big is the entire universe? So far, with our most powerful galaxy surveys, we've mapped out some 10 million galaxies of the suspected 2 trillion that inhabit the observable universe. We know that these galaxies twist and lace their way through filaments, intersecting at clusters and tracing a pattern that resembles a gigantic spider's web. This cosmic web is the largest pattern found in nature, filling up the observable universe from end to end, with massive voids left between the glittering braids. And pocking the cosmic web at these vast distances are subtle imprints. They are invisible to the eye and only reveal themselves as shells of slightly higher galactic density. These are the leftover echoes from when massive sound waves crashed around the very early universe. They're called baryonic acoustic oscillations, or BAO. A single BAO shell can be up to 1 billion light-years across. Just like the galaxies and the cosmic web, the size of the universe is determined by gravity. Indeed, the contents of the universe set the expansion rate and the time since the Big Bang. The rest is history. But the true extent of the universe is unknown. Indeed, for centuries, astronomers had believed the universe to be infinite. But of course, in an infinite universe that is also infinitely old, no matter where we look, we should see a star. Even accounting for the relative slowness of the speed of light at cosmic scales, with enough time, the sky should be ablaze everywhere with infinite light, even in the depths of night. And with the revelations of the Big Bang Theory, we discovered that the universe we can interact with is not infinite. It has an age, and because of that age, it has a limit. The universe is only so old, the speed of light only so swift. The sky is not illuminated with the light of infinite suns, because the universe is not infinitely old. In fact, the expansion of the cosmos carries galaxies away from view, permanently. At great distances, the recession of distant galaxies can exceed the speed of light. We can still see other galaxies, for now, but that's because their light left long ago. By the time their light reaches the Earth, billions of years later, the galaxy is long gone from view, carried away by the inexorable cosmic expansion. And so, the entire universe could be infinite. Perhaps we will never know. Like a lantern lit in a dark forest, our entire existence is defined by this sphere of feeble and flickering illumination. That sphere is 93 billion light-years, or roughly 10 to the power of 62 Planck lengths, in diameter. That is the distance to the edge of the cosmological horizon, the largest possible scale that we could ever measure in the universe. And all that exists on these largest scales, from the galaxies and the cosmic web to the ultimate horizon of the universe itself, was dictated long ago. For gravity may control the fate of the universe and be the invisible hand that sculpts the great creation, but it was not the instigator. It was not what set it all in motion. And this is linked to the biggest mystery in the universe. For at roughly 100 megaparsecs or so, the universe evens out. With no larger structures or differences from place to place within the cosmic web, this is called the scale of homogeneity, or, somewhat more dramatically, the end of greatness. This is the mirror image of the Planck scale, roughly 10 to the power of 59 times larger than its twin, the other end of the universe. At the Planck scale, reality is nothing but chaos. At the homogeneity scale, everything is the same. Why? At the very earliest epochs in the universe, when the entire observable universe was compressed to scales even smaller than the Planck length, unknown forces were in action. They set the universe in motion, and through quantum creativity wrote a story that would be told over the coming ages. And we call this event inflation. This is a hypothetical period that occurred when the universe was less than 10 to the power of minus 35 seconds old, and it was over and done with by the time the universe turned 10 to the power of minus 34 seconds old. In that briefest flicker of time, the cosmos became much, much larger, growing in size by at least 10 to the power of 50 orders of magnitude, reaching the comparatively dizzying proportions of an entire atomic nucleus. And so inflation made everything bigger, even the quantum fluctuations that only exist at the Planck scale. Now made microscopic, those fluctuations imprinted themselves on the fabric of space-time, leading to pockets of slightly higher density scattered across the vast expanses of the universe. And these were the seeds that started it all. What would follow would be the weaving of the cosmic web itself, the smallest possible fluctuations in the universe intimately connected through strands of gravity to the largest pattern in nature. And this is the homogeneity scale. These quantum fluctuations blown up to countless trillions their original size and averaged out across the cosmos. And so now, for the final time, we can return to the apple. An apple at this scale would completely change the course of cosmic evolution. It would take eons to play out, as sections of the apple splintered off and collapsed in on themselves, slowly imploding under their own weight to become galaxies in their own right. But at cosmic scales, a balance would shift. The present-day universe is ruled by dark energy, a mysterious force that is accelerating cosmic expansion. But even if we were to eliminate dark energy, or if it were to fizzle out and disappear, the expansion would not stop. There's simply not enough matter with enough mutual gravity to halt expansion. Indeed, the universe is achingly thin, with an average density of just 1 hydrogen atom per cubic meter. An apple, however, is far, far denser than that. An apple tens of gigaparsecs across would be more than enough to slow cosmic expansion, to halt it, and even reverse it. The future universe would then be smaller than the past, the Big Bang turning into a big crunch, with the endpoint a singularity of infinite density, the same mysterious state that gave birth to the cosmos 13.8 billion years ago. We do not know why the universe is the way it is, why it's filled with so much matter and so much dark energy. The present-day universe could have been much smaller, or much larger, had anything been different in those early quantum forges. There are only 4 known forces in the universe, and 3 generations of each of the particles. Together they dance and weave and intersect, sometimes colliding, sometimes colluding. At the smallest of scales, all the forces meld together into an incoherent mess, and at the largest, only gravity remains. In between is everything else. The atoms, life, the stars, the galaxies, each one bound by a set of rules that governs their respective domains. So perhaps that is the secret as to why the apple, and us, is at the center of the 62 orders of magnitude that span reality. We sit at the confluence of all the forces of nature, each one working in its own way to influence what happens here on the surface of the Earth. At the smallest quantum scales, gravity holds no sway. At the largest, the other 3 fall silent. But here, on the Earth, at scales of roughly a meter, everything comes together. The strong nuclear force binds together the atoms. The weak nuclear force transforms them and creates the table of elements. Electromagnetism holds electrons in their shells and glues the atoms together to make molecules and the dance of life. And finally, holding everything together is gravity, giving us a solid foundation under our feet and an anchor for our oceans and air. All the forces of nature, across all 62 orders of magnitude that measure existence, work together right here at the apple, the center of the universe. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave us a comment to tell us what you think. Thanks for watching, and we'll see you next time. Take a deep breath. There are about 56 stillion atoms in every breath that you breathe in. That's a 5, followed by 22 zeros. 7 octillion atoms make up your body. That's a 7, followed by 27 zeros. The whole of planet Earth is composed of 100 quindecillion atoms, or a 1, followed by 50 zeros. In the entire observable universe, 46 billion light-years across, there are thought to be up to 100,000 quadrillion vigintillion atoms, or a 1, followed by 82 zeros. And the biggest number in the cosmos can actually be arrived at by dividing the total volume of the observable universe by the smallest possible unit of volume, the Planck space. Dividing everything we can see into minuscule cubes, we end up with 1 times 10 to the power of 185 of those cubes. And yet that is not yet the biggest number that humans have conceived. Take, for example, the Goliath that is Tree 3. As Antonio Padilla, physicist at Nottingham University, puts it, everything you think you know is dwarfed into nothing. Welcome to the game of trees. You start with a coloured seed, which can give rise to a tree whose branches end in seeds that can sprout their own trees. The goal is to make as many trees as possible, and there are 2 main rules. The first tree must contain 1 seed, the second a maximum of 2 seeds, the third a maximum of 3 seeds, and so on. At each level, the tree can contain less than the maximum number, but that maximum is fixed to correspond to the level you're at. Secondly, the game ends and the forest dies if you create a tree that already exists within the forest. So if you repeat a pattern of coloured seeds that are linked together, no matter how far away it is in the forest, it is game over. Mathematicians have played this game with different numbers of seed colours. Tree 1 allows only a single seed colour, and the forest dies at the first tree. The second seed you add is necessarily a repeat of the first. Tree 2 can last up to 3 trees. Starting with 1 colour, you make a tree that contains 2 branches, both of a second colour. The next tree has just 1 branch. By the next step, all possible combinations of 2 colours have already been used, and you can't avoid building a tree that's already been seen. But then you come to Tree 3. Tree 3 uses 3 colours. Tree 3 is different. Whereas the previous forests died disappointingly quickly, a forest of 3 coloured seeds grows for an extraordinarily long time. Mathematicians have proved the game must end at some point, but they've not been able to count the trees it would take to get there. They've not been able to, because if they did, their brains would implode. As Antonio Padilla goes on to say in his exploration of huge numbers, for a while you feel nothing untoward, a string of digits growing larger and larger in your mind's eye. And then it happens. Just trying to imagine a number that large is more than the human brain can take. Trying to hold that number of digits in your head would result in a black hole forming from the sheer quantity of information crammed inside. Indeed, faced with all the digits of Tree 3, scientists believe that the entire observable universe will also suffer the same fate. And so, the solution to Tree 3 is, without a doubt, a mind-bendingly enormous number. But it is still a finite number, and so it is still smaller than infinity. In fact, however big the solution to Tree 3 is, it is much, much closer to 0 than it is to infinity. Whereas counting to the top of Tree 3 may be a foolish thing to attempt, it isn't futile, because there is an end. But infinity has no end. It just keeps going, without reprieve, For every digit, every object, every anything, no matter how large, there is another waiting in line, and another, and another. So, what happens when you keep going? Is the universe itself infinite? And what would it mean to live in a universe that never ended? Take a deep breath. Things are about to get weird. Albert Einstein once said that politics is more difficult than physics. Ground News have kindly supported this video, and they are the world's first news comparison platform. Because around 530 BC, in the small town of Croton in southern Italy, a secretive band of brothers meets in a lamplit room, whispering in hushed tones while they wait for their illustrious leader to make his appearance. Their conversation is impassioned and reverential, like that of any cult, but these men do not speak of gods. Their concern is with the human soul, of geometry, and above all else, numbers. As their master emerges from the shadows, his disciples fall silent to better hear his latest doctrine. For everything that the great Pythagoras utters must be the absolute truth. In ancient Greece, it wasn't uncommon for scholars and their students to worship philosophical and mathematical concepts, but the Pythagoreans took things to a new level. Believing in the transmigration of the human soul into the bodies of animals, followers were strictly forbidden to eat meat. As such, the cult were thought to be among the first ever vegetarians, although this would have been a challenge, as they believed a small part of a man's soul was lost every time he passed gas. Pythagoras preached that the only escape from this endless cycle of death and animalistic reincarnation was to seek higher knowledge of the universe. And so, the Pythagoreans built a doctrine around numbers. In their reverence of the rational, the Pythagoreans sought to support their worldview by demonstrating the utility of the counting numbers 1, 2, 3, 4, and so on, whereas unwieldy, ungraspable, irrational numbers were evil, defined by darkness and maleficence. In the cosmic battle of light over darkness, that which was unlimited was to be abhorred and avoided at all costs. But it was in geometry that the Pythagorean doctrine began to crumble. The closer they looked, the more they realized that not everything could be explained so simply. When attempting to calculate the length of a square's diagonal, there was no neat and tidy solution that equated it to a ratio of 2 counting numbers. The result was always irrational, always inelegant, perpetually troubling. The one thing that carried Pythagoras' name down through the centuries, the calculation of diagonals in squares and triangles, is the very thing that caused his cult such discomfort. Irrational numbers were an unavoidable part of our reality, however disturbing that was, and among all numbers, none was more disturbing than infinity. Over the coming centuries, philosophers who were not so rigid in their mathematical doctrine as the Pythagoreans began to contemplate the concept of the truly limitless. Take, for example, Zeno's paradox, named for another ancient Greek. Picture any journey you must complete, like the journey home after a long day at work. In order to go home, you must first travel half the way there. Then, to cover the remaining distance, you first have to travel half of it, bringing you 3/4 of the way home. Traveling half of the next stretch completes 7/8 of the journey, and the next half brings you 15/16 of the way home. Following this principle of splitting each stretch of the journey into halves, you can continue traveling halves an infinite number of times and never reach your destination. This situation wouldn't happen in reality, of course. You would make it home after work eventually, but there is no doubting the logic of these infinite divisions. Many Greeks tried to reconcile this by relegating concepts of the infinite to the divine and metaphysical, claiming that they weren't a part of the rational world. However, others tried to categorize infinities themselves. There was a difference, they claimed, between an actual infinity, which is an infinite quantity of things that exist exist all at once, and a potential infinity, which only comes into existence as a result of a process. So, counting to infinity, or subdividing a journey an infinite number of times, are potential infinities, whereas actual infinities, like an infinitely large object, were still despised and refuted. They were simply impossible. Some 2,500 years have since passed since this ancient introspection, and with it has come waves of mathematical and scholarly advancement. No longer tied to cults or secret societies, numbers could be analysed for what they really were, rather than what they signified. And the same was true for our ideas of infinity, marked by a huge leap forward in the late 19th century by a German mathematician named Georg Cantor. Cantor was the first to consider that there truly are different kinds of infinity. He described how there are an infinite number of counting numbers, but also an infinite number of even numbers too. Both groups are infinite in size, despite the fact that the list of counting numbers completely contains the list of even numbers, plus the odd numbers as well. This apparent paradox is possible purely because of the bizarre nature of infinity. Each of the even numbers can be put in a numbered list, paired with a corresponding counting number. So 2 is number 1, 4 is number 2, 6 is number 3, and so on. Right up to infinity. You'll always be able to match an even number to a counting number. So they are both the same size. But Cantor also showed that there are actually infinities of different sizes when you consider subsets within an infinite number of counting numbers. Take the 4 members of the Beatles, John, Paul, George and Ringo. How many different combinations or subsets of members could you form from among this group? You could have each of the 4 by themselves, pairs like John and Ringo, or Paul and George, trios like John, Paul and Ringo, and you can have a set of 0, no Beatles at all. In total, there are 16 possible configurations of the 4 Beatles, many more than the original number. And the same applies to infinity. Because of this multiplying nature of subsets, there will always be more subsets than there are counting numbers. There are indeed infinite sets of infinite counting numbers, but one infinity is necessarily larger than the other. If you find this to be twisting your brain to breaking point, you're not alone. Georg Cantor himself suffered several nervous breakdowns over the course of his career and spent the last year of his life in a mental hospital. Nevertheless, we must continue to consider the infinite if we hope to understand the past, present, and future of the cosmos. For all their complexity, Cantor's transfinite mathematics and the Greeks' desperate reasoning with impossible paradoxes were limited to the contemplation of numbers alone. The Greeks desperately tried to avoid any contact between the infinite and reality, but astronomers now find themselves confronted with actual infinities at every turn. From the infinite densities at the heart of supermassive black holes to the potentially infinite expanse of the universe as a whole, scientists are now equipped with the mathematical and practical tools to tackle these problems head-on and face the many oddities of an infinite cosmos and what they would mean for our tiny, fleeting existence. A young man surveys his home with wary eyes as he pushes through the undergrowth on North Sentinel Island. Brushing his hand lightly across the leaves as he passes, he recognizes each of the trees, bushes, and craggy rocks. They are as familiar as the faces of his children. Gradually, the trees thin and open out to a sandy beach, beyond which is a vast expanse of blue. He knows this land, this beach. He's even fished from his boat in the shallow waters not far from shore. But the ocean extends far further than the shallow canoe will ever be able to carry him. It plunges to dark and unfathomable depths, and it stretches out and encircles his island with a solid halo of blue. This is the man's entire universe. The island is his world, and everything he can see is all there is. And yet, one afternoon, when he and his companions are bringing in the day's meager catch, something new arrives in the man's universe. It's a white speck, at first too small to make out at the edge of the ocean. It gradually grows in size as it approaches the island, and before long it casts its long shadow into the fishing waters. The young man and his brothers are justifiably terrified of these new alien beings that have descended silently into their world. They throw rocks and sticks at the gigantic vessel before retreating back under the cover of trees. Had the Sentinelese man been focused on anything other than repelling the immediate danger, a flicker of curiosity may have come to him. If the island and its ringing ocean was all there was, then where did these aliens and their giant vessel come from? If he had peered back out from the safety of the trees at the end of the day, he would have seen the white boat shrink and then disappear beyond the horizon of the man's own universe. Was there a vast expanse that lay beyond his own observable cosmos? Scientists and philosophers have long grappled with the concept of an observable universe and what, if anything, lies beyond. As early as the 4th century BC, the Greek scholar Archytas considered what it would be like to travel to the edge of the heavens and then extend his hand out beyond the limit. There could be nothing greater than the heavens themselves, and so this, he claimed, clearly implied a space without limit, an essentially infinite universe. In the 16th century, Italian philosopher Giordano Bruno also concluded that space was infinite and contained infinitely many things, a statement that, unfortunately for him, angered the church. Bruno was captured, tortured, and eventually burnt at the stake. Never had contemplating infinity been so mortally dangerous. And so, in the following century, the English philosopher Thomas Hobbes came to a much more acceptable conclusion on the nature of the infinite universe. It was meaningless to speculate, he said, whether there is or is not an infinite cosmos beyond what we can see, because there's simply nothing we can do to measure it. Better to put the idea to bed and concern ourselves with the many mysteries that we can see, rather than those we never will. Whether through self-preservation or genuine conviction, his assertions have echoed down through the centuries and are still repeated by scientists to this day. Why speculate when nothing good can come of it? Although you're unlikely to lose your life over the matter these days, you may still lose your mind. Nevertheless, a few brave cosmologists still choose to risk befuddlement in tackling the potentially unknowable. Today, we have better tools than ever to probe the observable universe and centuries of science, mathematics, and philosophy to cling on to as we contemplate the potentially infinite reality of what lies beyond. Like the tribes of North Sentinel Island, our view of the cosmos is limited by how far we can see within it. Light never travels faster than about 300 million meters per second, and so the further we look in space, the further we are looking back in time. We can see galaxies from 1 billion years ago, from 5 billion years ago, even from 10 billion years ago. But at a certain distance, the light fades away. We see no more galaxies, because this long ago, there were not yet any galaxies to be seen. The edge of our observable universe is therefore defined as much by time as it is by space. It is not a physical construct, just a measurement of how fast light can travel. And the distance to that edge is further defined by the expansion that has taken place since those first galaxies started growing. Their light has been traveling for 13.8 billion years, so they are at least 13.8 billion light-years away. But in the intervening period, space has continued to expand, and so those first galaxies are now some 46 billion light-years distant. Though when we probe the limits of our observable universe, it is very clear just how little the edges look like edges. There is nothing in the structure or distribution of these distant galaxies to suggest they're all piled up against an invisible barrier, even though it is vanishingly unlikely that the cosmos began with a perfectly even distribution of matter and energy. On the broadest scale, that is what we see. There is no center to the universe. On scales above about 230 light-years, wherever we look, there are no places that are any hotter, colder, or more or less densely clustered with galaxies than anywhere else. Using the cosmic microwave background, a universe-wide afterglow from just 300,000 years after the Big Bang, affectionately known as the universe's baby picture, scientists have found differences on the largest scales of barely a couple of parts in 100,000. In fact, this homogeneity is considered strong evidence for the cosmological period of inflation, a fraction of a second at the beginning of time when the universe is believed to have doubled in size some 80 times, thus expanding away many of its smaller wrinkles. And so, by taking inflation and its resulting homogeneity into account, despite the vastness of a universe 92 billion light-years in diameter, it really must be much, much larger if it is to contain the inevitable irregularities of the early universe. As Thomas Hobbes said, though, there is nothing we can do to probe that distant expanse, and no amount of modern technology will change that. We are forever limited by the speed of light. But we do have an almost infinite capacity for imagination, and meaningless or not, we can speculate about exactly what lies beyond.